Here's the Lecture 7 Q&A. Since the lecture was mostly about exam review, almost all of this Q&A is going over old exam problems. We will have another Q&A on Monday at 9 a.m. in case students have more questions about old exam problems or want to ask about the practice exam, which will be released today. At the end of this video, there is a description of everything that's happening over the next 4 days. So if you're wondering whether you're missing out on anything, you could watch that and make sure that you're not.
Okay, so thanks. The question is, how do you go about solving question 6A from the fall 2018 midterm 1, which here it is on my screen, and we'll have to read it, and then we'll have to think a little bit, and then maybe we'll figure it out.
John, can I interrupt just 1 second? A question on the chat, just so I don't forget about it. Somebody's asking if there is a limit on the font size on their 2-page notes.
Yeah, there is. It's written in there that like a 6-point or larger would be nice, I think. So it should be legible by a human being.
All right, legible and by not just somebody with 20/20 vision. So,
but yes, you can make it very small. That's fine. Okay, a repeatable integer function takes an integer argument, returns a repeatable integer function. Implement repeat, which is a repeatable integer function that detects repeated arguments. As a side effect of repeated calls, it prints each argument that has been used before in a sequence of repeated calls. Therefore, if an argument appears n times, it is printed n-1 times in total each time other than the first. The detector function is part of the implementation of repeat, and we have to figure out how it is used. And we can't use things that we haven't covered in the course yet. So we have to somehow do this using just higher order functions. So we got an if statement, that'll probably be helpful. And detector is a function that takes something and probably will print it out. So yeah, I wonder if it's worth just trying to do this in Tutor so we can see what's going on. I have not looked at this question in some time, but I bet we'll work it out. All right, I think that's how we start. First of all, just look at the example. It's always a good way to go. So we call it on 1, nothing gets printed. Call it on 7, nothing gets printed. There's the second 7, so the 7 gets printed. Then 3 and 4 come for the first time, 2 and 5 as well. Then we see another 1, so that gets printed because there was a 1 long ago. 6 is the first 6, but this is actually the second 5. And so that one gets printed and this 1 gets printed. So I would strongly recommend it whenever you're trying to work on a problem and you think you understand what it's asking, that you look through an example and make sure that it behaves like you'd expect, because it's often the case that you try to solve a different problem than we'd like you to solve, and checking the examples can help with that quite a bit. I'd also say this is like one of those particularly difficult questions where most students skip it, and that's fine because you could still get an A in this class skipping the hardest problem on every exam. But if you want to try it, that's also great. So let's work on it together. So rather than diving into repeat, which I think is just going to like call detector and set it up right, the real work is to figure out how this is going to go. So it does seem like we have the following available to us. We have I is typically a number, f is typically a function, so let's assume it's going to work out that way and we can change our plan later. We have this g function, which I think could be the result of this, is we get back a g function which is ready to take another number. So let's say I might be 7. And we need to figure out whether I is something we've seen before or we haven't seen before. We don't actually have a list of all the things we've seen before or like some way to peer into the past. All we really have is some function. So in that case, let's hypothesize that this function tells us whether we've seen I before and work with that for a while. And then we can try to engineer it so that it does exactly that. So if f is a function that tells us whether we've seen I before, then we just call it to figure out whether we'd seen I before. And if it returns a true value, then it's time to print I. How would we set it up such that this is a function that tells us whether we've seen something before. Well, since g gets called on 7 and gives us back a function that we can call on something, it does seem like we need to return a function here. That's the common pattern with repeatable functions, is that a function can return another function, and I'm not going to return g because I want to somehow remember that I've seen I in the past. So that kind of limits me to returning a new function, a function that we can define using a lambda expression, because I don't see where else we could put this. So this lambda expression means that we're going to get in some new value later. What are we going to do with this function? Well, I think what we're going to do is build a function that detects whether we've seen I. Oh, this is interesting, because here's a function that tells us whether we've seen I before. If we just passed that in as a new value for f, then the next g would be able to detect whether it saw I before. I think this gets us part of the way there. This isn't the full solution, but it's something. So I think maybe we'll run this, try to understand how it's working, and then figure out how to fix it. But first we have to figure out how to repeat. So I think when you repeat, probably you start out with a detector that's never seen anything before. Any j you pass into it, it says, nope, I've never seen that before. And then we'll call that on the number 1 and find out that we've never seen it before, but that will kind of get the process going. Oh, we need to actually call this. So let's call this on repeat 1, 7, 7, and we'll worry about the rest of the example later. So when we call repeat on 1, we call detector on a function that says, I've never seen anything before. And that builds a new function, g, which is the printer, right? If you look at the body of g, it says it's going to print things. Now, this expression up here doesn't just call detector. It also calls the result of calling detector on k. So that would be the g function. So the reason that we see a g frame here is because of the parentheses that contain k, and k was bound to 1 in the repeat frame, and therefore 1 is the number that's getting passed in here. We've never seen anything before, so we don't print, but here we do build a detector that has seen I before. So what happens to this detector that we built? Well, it gets returned as the value of repeat 1. So here we see g getting called on the next argument. So at least we've built like a repeatable function structure, where basically every time there's a parenthesis with a number in it here, we're getting another call to g with that new number. Now we see a 7. 7 we've never seen before. So we return yet another g. Wow, this is getting long. Maybe doing this in Python Tutor wasn't a good idea, but I think we'll see something printed pretty soon. So here's the third g from the third call. Sorry, that's not on the screen at the same time. And this time, since we saw 7 before, we're going to see 7 printed. Oh, there it is. So it detected that the same number was twice in a row. So let me pause there. I'm guessing people have questions about this specific code. If you have a question about something else, then wait on it. But if you have some question about like exactly what I wrote here, I know this is not a complete solution. We'll finish it off in a minute, but we have been able to detect when there's the same number twice in a row, and that's interesting. But how we did it is obviously kind of convoluted. So let's talk about what's here, and then we'll solve the problem. Good question. So the question is, where did this lambda j false come from? I had, like, when you see a functional argument, you have to ask yourself, what is it doing? And that's really the key to unlocking one of these problems and making progress. What this is doing is it's telling us whether for some new I, we've seen it before. That's what f is doing. So every time I call detector, I should call it with a function that tells me what I've seen before. At the very beginning, repeat just gets called at the very beginning, and we never call repeat again. At the very beginning, we've seen nothing before. So that's why we come up with a function that takes in any number and says, nope, I've never seen it before. So that no matter what the next number is, which will really be the first number, we don't print it out because we've never seen it.
Yeah, so the way to think about it is look what detector takes as input. So if you look on line 10, that's the initial call, which is basically saying I haven't seen anything. And then look at line 16. Every time you call detector, you're calling it with a function that tests the equality. Yeah, so on line 16, that's testing J and I, which isn't, again, quite the full solution yet, but it'll get there. So you got to sort of bootstrap this process, and that's what that first call is doing. And then it sort of takes over and keeps repeating and repeating and repeating on itself, eventually doing the check.
And it wouldn't be crazy to make a note if you're solving this, that this needs a better name, like have seen I before would be like a reasonable name for this function.
A follow-up question was, what is the j in the lambda j on line 16 going to be?
That's going to be the parameter to the function, right? So you're returning a function, not evaluating it. Yeah, that's not a function call. Notice there's no parentheses after that lambda. So you're passing to detector a function. That function takes as a parameter j and returns whether j is equal to I, where I is instantiated based on the environment that that lambda is defined in.
Exactly. Like a good way to think about these names that come right after lambda or inside here is these are numbers you don't know yet, but you will know them sometime in the future. In this case, j is going to be the next thing that gets passed in. I can't tell that just by looking at this line of code. I have to look at all the code and see what will happen to it. But in principle, you even just by looking at this code here, you know j is something that you'll know later. And you don't know it now. So you're like creating this placeholder for something you'll know later.
So Kaylin's asking in the chat, why the K on line 10? So I think the question, if I'm understanding, so this whole thing starts off by calling repeat with some value, yeah? And then, so look at the line 19. So let's parse that. We're calling repeat of 1. That must return a function, yeah? Because it's then going to be called on 7, which must return a function because that's going to be called on 7. Yeah, does that make sense? Well, okay. I'm talking to the chat room now, John. So
yeah, I think that's a good explanation. I mean, another explanation is that if instead of writing repeat, we could have just written detector that tells you it's never seen anything before. Oh, sorry. And then start giving it inputs. That would have been another way to achieve the same thing. So if you want to kind of bundle this up into a name, we could have just like given it a name, but instead we've created a function that takes an argument. And that means the definition of repeat is going to have to cover all this stuff and do that piece.
Yeah, so notice 1 is not the parameter j in that lambda expression. Yeah, that lambda expression goes into detector, it's a function. Detector returns a function to us, and then that gets applied to 1, which returns, okay, we got an okay in the chat room. I can stop talking now.
All right. So let's figure out what's wrong with this solution, which is that it only looks for adjacent things. So if I wrote 7, 1, 7, I think we would run into trouble. So in the description of repeat, this is supposed to print, but if we just crank for a while, we'll see, oh, it did a lot of work and it never printed anything. And that's because the function that we're passing in as the new have I seen it before just tells you whether you just saw it, whether it was the previous I. And you really want to know whether you've ever seen it. So J is something I've seen if it's the same as the thing that I just saw, or if it's something that I saw before that. Fortunately, we have a function to tell us whether we saw J before that. This time, it prints the 7. Or if we try this long example, hopefully it will print 7151, or we'll crash, one of the two. Oh, it crashed. All right, let's do a little shorter example. Let's make sure we get at least the 7 and the 1. How about that? That worked. All right, so here we go. Crank, crank, crank. It got the 7. Crank, crank, crank some more. And it got the 1. So I think this, aside from the fact that we changed the name, is a solution to this problem where the story is, forget about this for a while, build a function that tells you what you've seen before and returns a function that takes in something new, and if you've seen it before, print it. Then build a new function just like G, except for the F that tells you what you've seen before shouldn't just be the old F. It should be a new F that takes in J and checks not only against everything that's been seen earlier, but also the thing you just saw.
By the way, notice the brilliance of what John did earlier when he changed the name of F to have seen I. Look at how much easier it is to understand the code when you understand that what F is actually doing is asking, have I seen I before, as opposed to some generic F. So when John first wrote this, he said, well, okay, we want to know if J is equal to I, but we also want to know if we've seen this before. And that's the power of abstraction. Once you decide what the function does, just do it. Trust that that actually works. And there's something very clever about that's why it's sort of good to use clever or meaningful function names, because it helps you think through the logic when they're particularly convoluted like this.
So there's no doubt this is kind of pushing the limit of what we've learned in this course so far, and
I would say more than that, John. I think you have pushed the limit.
And so, yeah, I mean, there is often a kind of a question that's there to sort of figure out who's really mastered every single way that you could possibly put this together. Most of the exam doesn't look like this, so don't spend all your time just focused on examples like this. Much better to spend your time making sure you're going to get the more straightforward questions correct, and ignore this question completely, rather than just kind of drill yourself on this kind of thing. But it is interesting to see that it is possible to do this using the pieces that we have.
Yeah, somebody asked the question earlier about how these lambda expressions retain state. Yeah, and that's basically what we're doing here. John said earlier that, look, if I had a list with a bunch of numbers in it, this would have been trivial. Yeah, go to the beginning, work your way through and look for the number. And so by virtue of building up these lambda expressions on line 16, where the variables are being instantiated, you are building up this notion of a state. And that is sort of tricky and hard to see, yeah?
Yeah, every time you build a new function, it's got a little bit of an old function in it.
Yeah.
And some other stuff. And that is that kind of construction we're going to see a lot more in the course in the future. And you'll see, throughout your studies of computer science, that oftentimes you sort of build things up incrementally. And that means that every time we call this, we've got a more interesting function than we had before, because at the beginning, it was really simple. It just didn't know about anything. And then it knows about 1, and then it knows about 1 and 7, and then it knows about 1 and 7 and 7. Well, 7 is the same, but you get the idea. 1 and 7, then 7 and 3. And that's kind of how it's accumulating a more and more elaborate function. You could write this directly. You could write I want a lambda j that tells you whether I've ever seen, let's see how I'm going to do this. The first version, have seen 0, looks like I've never seen anything. And have seen 1 looks like I've only seen 1, or whatever have seen 0 has done. And then the next one has seen 7, or whatever have seen 1 has done. This is essentially what we're doing in building up our have seens, is that we're chaining together functions in order to build up something more interesting. This one's going to return true if you pass in 7 or 1, whereas this one would only return true on 1, and this one would always return false.
Two quick things, and then we're going to move on to some more questions. Somebody's asking, let me find the question. In line 16, how is it that 2 functions are passed in as a parameter? There are not 2 functions there. You are returning the result of calling detector on a function that takes a single parameter.
Yeah, it would be equivalent to write that.
Good, thank you.
And so this says, return one thing, whatever detector returns. And what detector returns is just G. So this says G is going to return G. It's just not the same G. The code is the same, but the have seen function is different. It's seeing more stuff. It's getting older, right? So this basically is very similar to def G of I return G, except for we're getting a slightly different version of G each time, the result of calling detector again, which returns G, but with a new have seen. All right, let's make sure we don't have to read any of this. I don't think there's any sims or alarms or anything mentioned here. Okay, so it's really just down to this much code and what happens when you call pumbaa on Timon and 5. Let's take a look. Pumbaa is a function that takes another function, then takes an argument and calls f twice on x. So it says. Now we're going to reassign pumbaa to something else. So let's just pause for a moment and first understand that if we didn't have this assignment statement, life would be a little bit simpler. We would take Timon, call it on 5, take that result, call Timon on that, and we'd be done. But this actually says, take pumbaa and call it on itself. Well, what does that mean? That means create a version of pumbaa where this is already filled in. We've filled it in with pumbaa, which takes functions and calls them twice. So that means since we have already filled in the f, we are going to take one more argument x, and that needs to be a function that we can then apply twice. So this says effectively apply twice the function that applies things twice. So when you actually pass an argument into that, it's going to be applied twice, or applied 4 times. Okay, Rafiki is set to 1. Timon is fortunately less insane. It just says a function that adds Rafiki to y, whatever its argument is. Now it is true that between when you define this function and you call this function, if you change Rafiki, that change will be reflected in the behavior of Timon. And why is that? Well, this expression is going to be evaluated whenever this function gets called. And when you evaluate it, it uses the current values. And we didn't call it here, we just defined it. So Rafiki -1 is the thing that we're going to use. Okay, so now let's try to read this. This says, apply twice, or apply 4 times the Timon function to the number 5. And what does the Timon function do? Well, it actually doesn't add 1, but subtracts 1 because of this change. So we're going to subtract 1 4 times to the number 5. So 5 subtract 1 gives you 4, subtract 1 gives you 3, subtract 1 gives you 2, subtract 1 gives you 1. I think it would come out at 1.
And Raymond, let me suggest one other strategy. I mean, this is, you sort of have to learn sort of how and when to do this, but what makes this problem more difficult is that second line, the pumbaa equals pumbaa of pumbaa, right? So if you just cross that out, it's a pretty approachable problem. And that's what I would have done. I'd be like, all right, that's clearly the line that's going to make my life miserable. I'm going to delete that for a minute, make sure I understand how Pumbaa is working, make sure the Rafiki, where it gets instantiated, work through all of that and be like, okay, I now understand what this is happening, and then add that other level of complexity. So you breaking down the problems, John did this earlier where he sort of solved the slightly wrong problem and then went back and fixed it. Somebody's asking why we're using -1 for Rafiki. And the reason is that on that line, Timon equals lambda, you're not calling the function. You are defining the function, which means that the parameters in the body are not instantiated until you call it. At the time you call it, which is after Rafiki has been reset to -1, then that is the value. And John's about to show us right now.
Yeah, exactly. Sorry if I was distracting. I was just trying to illustrate what you were saying, which is that eventually you're going to evaluate y plus Rafiki, but not until you start calling Timon. And at that time, Rafiki is -1. The process is always, when it's time to evaluate y plus Rafiki, you look for y, you look for Rafiki, and you add those together, you get.
And okay, and somebody's asking, is drawing the environment diagrams for these problems too much time, or is it recommended? John, what do you think? You have more experience with these exams than I do.
You know, it wouldn't help you here. Environment diagrams are a great way to precisely describe everything that happens inside of a program. But when a lot is happening inside of a program, they become complicated enough that, you know, you're more likely to make a mistake than you are to understand what's going on. Yeah. So you'd be better served in this case just describing what Pumbaa does, and then asking yourself, okay, what would Pumbaa do if you apply something twice and you apply that twice? What does that mean? That means apply it 4 times. You know, that was a lot faster reasoning than drawing an environment diagram, which I suspect would be substantial for this problem.
Yeah, I think so too. Somebody's asking if WWPD questions are going to show up on the exam.
I won't just ask you what the Python will do, because we're giving you a Python interpreter, so you would hopefully be able to answer such a question. Though we are going to try to test the same skill. Usually we do it like I described in the lecture videos for today, that we'll just ask you to describe a function. Like, you know, what does this do? So I might give you this example, and you know, if I gave you these 2 lines and I said, which of these descriptions is correct for Pumbaa? It takes a function and an argument and applies the function 4 times to the argument, or 2 times, or it ignores the argument, or whatever. You should be able to answer that descriptive version.
Great. I'm sure you all have good test-taking strategies, but let me just emphasize one thing. There's going to be some problems that you can whiz through and some you can't. Don't get bogged down on the ones you get stuck on. Don't blow 15, 20 minutes on some little 2-pointer. Like, you go through the exam, get done what you can, and then go back and deal with the hard ones. And there's always going to be one, like, you know, killer question. Don't go crazy on those. They're fun. You can do them later, but don't sacrifice the rest of the exam for it.
Yeah, it's probably better to check your work on the stuff that you're more comfortable on than it is to think deeply about Pumbaa or something like that, because you know, most of the points is up here.
I think I know the answer to this, but let me verify. Somebody's asking if we're allowed to go back to questions on the exam. Is the exam going to be one? John, you and I talked yesterday, but I can't remember what we decided.
Yeah, this is right. So you just get the whole thing, and you can spend your time however you want.
Yeah.
I would say that we've now given a few exams where students have an interpreter available, and I don't think it's helped students very much. I think that there's a big risk that if you just try to like run your code over and over until like some test case passes, you'll lose a lot of time. You know, these exams are best solved by like reading and thinking, as opposed to trying to get like your environment all set up and running the code or something like that. So if you're thinking about how to spend your time, I would recommend working through the exam without using code.cs618.org or tutor much at all, and kind of save that for when you're going to go back and address the ones that you couldn't do the first time. But if you can just like work your way through, you know a lot about Python and how it works, you know a lot about how to solve problems, do the stuff you can that doesn't involve like running anything, then that's probably a much better time management strategy than like trying to get all the tests to run and stuff like that.
John, since there are no other questions, somebody's asking in the chat if we can explain pumbaa one more time. Do you want to just walk through that really quick?
Yeah, let's see if I can try it again. When you have a function that says, give me something, what I'm going to apply it to, and apply it twice. This gives you something. Doesn't tell you what you're going to apply it to. That comes later. But it says, the thing that we're going to apply to Timon is to apply a function that makes it happen twice. So maybe we could look at it this way. At the end of the day, if you have pumbaa, and then what we had pumbaa, Timon. Oh, sorry, I forgot it. 5, right? I could have just written this.
Yeah.
The way you evaluate this is you figure out what you're going to call on 5. To figure out what you're going to call, you have to figure out what this is. Okay, so first we have to figure out what we're going to call. This is apply 4 times, because that's what it means to apply something twice. Timon to 5. So here, you're basically building a Timon function.
I like this explanation the best.
And then you finally call it on 5.
Yeah. So when you have a variable equal to something, being assigned to something, you can just take that thing and shove it where you're using it. And that sort of deals with this sort of almost like recursive-like definition. Yeah, so I like that the best. John, there's a number of questions in the chat about the time for everything, like the preps and the, can you just go through that one more time? Because I think there's a little bit of confusion about the timing for everything.
Oh, great. So here's what happens in the next 4 days. The first event is at 1 p.m. today. There'll be some announcements for a practice midterm, which is totally optional, but I recommend trying it if that fits into your schedule. The password to unlock that will be released at 1:10, and you'll have until 2 o'clock to work on it. So you'll have 50 minutes. It's a shorter length version of the midterm, similar kinds of problems, but just not as many of them. At 2 o'clock today, well, it'll start at 2:10. We'll have an exam prep section, which is just like a big Zoom webinar. You can find a link on. That'll probably run until 3 or 3:30. Sometimes they run over. And that's independent, but we'll cover more exam problems and strategies from a TA's point of view. Derek, who's running it, has TA'd this class like 6 times or something ridiculous, so he's quite good. Then we'll rerun the practice exam at 7 p.m. It will be identical to the 1 p.m. It's just an alternate time. Then nothing happens till Monday. Actually, there's some student run sessions over the weekend if you want to go to them.
You all study over the weekend. That's what happens.
Yeah, you could study. You could get some sleep. That's a good idea. Monday morning, we'll have a Q&A session. Nothing happens 2 p.m. Monday. 7 p.m. Monday, we'll run the exam. And so the announcements will start. The exam will be available. And, between 7 and 7:10, it's mostly like announcements and stuff like that. Get there at 7, but we'll release the password to unlock the exam, meaning you can actually start working on it at 7:10, and then you'll have until 9 o'clock to finish the exam.
And how are the passwords going to be released, John?
And post it on Piazza.
Okay, so on Piazza to the person who asked in the chat room.
Yeah, and if you feel like this description was short on details, well, maybe it was, but like every possible detail is in this Piazza post here.
The next question was, does it really make sense to try to come up with your own implementation for an exam question that doesn't match the template? This strategy was suggested in the lecture videos, but it might take too much time.
So I'll give you my answer and then we'll hear what John says. My answer is if you're completely stuck, you just look at the problem, you look at the framework, and you just don't know where to go, then I think writing it on your own is probably the right path, because otherwise, where do you go from there? If you're not completely stuck, you sort of basically see what it is, then I would say muscling through getting it to work is probably the right approach.
Yeah, the way we score these things is that you don't really get points for effort. You get points for doing things correctly, and you don't have to fill in every blank correctly in order to get points. But you do have to have things that are consistent with the right answer. And so it's better to like actually solve the problem than it is to think like, oh, what could I write that might get some points, typically. And in that sense, like, it takes much less time to read the exam than it does to take the exam. People who have been taking a lot of these exams can often finish them quite quickly relative to the time limit that we have. So there is time to think and to try stuff out and to backtrack a little bit in the design of the test. And there's time to go through the whole process of, looking through the examples and making sure you understand what you're trying to solve. And I think that there's, maybe not for all the questions, but for the ones that require it, there's time for you to kind of think about how would I write it independently of the template that's been given, because that can give you insights of like, oh, I see in my version that I'm comparing I to 0. I need to do that somewhere in the template. And then you can ask yourself, like, where in the template could I do that? And you fill that in, and then like you'll at least get credit for that part, that like piece of the logic, which is that you're like comparing something to 0. I know I'm just talking in the abstract. I'm not talking about an actual problem, but sometimes that's the right thing to do. This is much more effective than saying like, oh, in lots of past exams, I saw people comparing stuff to 0. So why don't I just put that on every line? The chance that you'll kind of guess the right logic is lower than if you actually know, oh, here's like a piece of the logic that I know I need. I'm going to figure out where to put it. So I do think it is effective to figure out how to solve the problem, even if you don't do it in our way. In midterm 1, there aren't like that many ways to solve these problems. So I wouldn't expect that you'll come up with like a perfectly good answer that is completely different from what the template looks like. Good luck, folks. Have fun studying. Rest up.
Thanks, everybody. See you on Monday. Have a good weekend. Try not to breathe the air.
Yeah, right.